All right, I just want to go over a couple of the examples in the probability 5 binomial distribution lesson. I won't cover the explanation of the concept or the formula here. That will be done in your classes. The only thing I will point out is that the conditions for a binomial distribution are that there must be a fixed number of independent trials, where on each trial the outcomes can only be success or failure. All right, so skip ahead to the first problem. As you can see, it says the records show that 6% of the items assembled on a production line are faulty. A random sample of 12 items is selected at random with replacement. That's obviously key as well, because it has to be independent trials. And we're going to find the probability that none will be faulty. All right, so using our probability notation, we actually want to find the probability that the discrete random variable x equals 0. So again, in this case, the event x is that there are no faulty, all right? Or the probability of an item being faulty. And so the formula, which you'll learn about, will be this way. It's the number of trials and the number of successes that we're looking for. And in this case, success is no faulty, and it's the probability of success, which in this case again is faulty, so 0.06, raised to the number of successes, and then the probability of failure, which has to be the complement of success, which in this case is non-faulty, so it's 0.94, and then it has to be raised to the number of successful failures in this case. So if you punch those numbers in your calculator, obviously 12C0, the first value is 1. 0.06 to the 0 equals 1. So really this equation boils down to 0.94 to the 12, which has a value of 0.476. We can do it on the calculator here really quick. 0.94. That's right. All right. 0.94. So 0.94 to the exponent 12, yeah, 0.476. Now the other way you can get that is with your calculator. We're going to use the feature called Binomial PDF, which calculates a particular probability in a probability distribution. I'll show you how it works. Simply go to the menu. We're going to go probability, option 5. It's a distribution, so it's in 5. And then it's not visible here, but if you scroll up, you can get to it fairly quickly, and you'll see it there. It's option D, so you can actually just choose the letter D, but it is Binomial PDF. It's a particular probability that we're looking for. That's how you remember it. So it's PDF, select it. So this, just try again. 5, 5, and the letter D for PDF. And it brings up the dialog box asking you for all these inputs. So the number of trials in this case is 12. The probability of success on each trial, 0.06. Again, in this case, success is seeing a faulty. And then the x value that we're looking for is 12, no faulties. So 0. All right, and there it is. 0.476, obviously the same answer, has to be. In part B, the probability of at most 1 will be faulty. So in this case, it's probably that x is less than equal to 1. It can be calculated as, you could do each one of these individually. It's the probability that there's no faulties plus the probability that there's 1 faulty. So you could do both of these as the same as the calculation that was done above, and add them. But again, the calculator can do this for you. And we're going to use the feature Binomial CDF. And CDF is cumulative. That's how you remember the C. It's cumulative. So it's when you want to add a bunch of probabilities together. They have to be added in order though, all right, from smallest to biggest. And so again, what you're going to do is on your calculator, you're going to go to menu. It's in the same place, probability distributions. If you scroll up though, you'll see that it's option E, all right? And now again, the inputs are the same, similar, it's a number of trials, so it's 12 trials. The probability of success, again, we're thinking of success as a faulty item. The lower bound is 0, that's correct, and the upper bound is 1 in this case. All right, and so that's 0.840 to 3 significant figures. Notice how it's printed out on the calculator screen of your calculator. Those are the inputs that you gave. 12 trials, 0.06 probability of success, and you're adding up 0 and 1, or from 0 up to 1. So again, if it said at most 2 faulty, then you put your lower boundary as 0 and your upper boundary as 2. All right. But again, the entry here was 12, comma 0.06, comma 0, comma 1. Again, you don't have to enter that. The calculator does that automatically when you put in the inputs. In part C, it says at least 2 will be faulty. So for at least 2, it's going to be greater than equal to 2. And just to show you here, greater than equal to 2, that can also be written as the probability of x being greater than 1. That's equivalent, all right? But again, what this means is it's the probability of x equals 2 plus the probability that x equals 3 plus, and then all the probabilities up to x equals 12. So obviously, this is not a calculation that you would want to do all these individually, especially when there's a high number of trials. So again, what we want to use is we want to use binomial CDF. It's accumulation of probabilities. And again, if you go to your calculator, again, we'll go menu, option 5. It's letter E this time. Okay, the number of trials is 12. The probability of success on each trial is 0.06. The lower bound this time is 2. We want to start adding at 2. And we want to stop adding at 12, up to 12. And we go, okay. And there it is, 0.1595. So again, you notice the calculator shows that this is your entry, 0.06, comma 2, comma 12. And that answer is 0.160 to 3 significant figures. And then the last one, very common, very commonly asked question on IB exams, for at least 1 faulty. So at least 1, always think of at least 1 as the opposite of none, all right? So we want the probability of x greater than 0, all right? And another very important concept, or actually, and this can also be written as x greater than equal to 1. That's at least 1. And it's very important that you can think of at least 1 as complementary to none. And the way you can make that calculation is 1 minus the probability that x equals 0. That's how you can do this complementary event. But again, in this case, we want the probabilities of all the x values from 1 up to 12. Again, a lot of individual calculations if you did it that way. So again, what we want to do is we want to use the binomial CDF feature on the calculator, and it'll be 12, 0.06, and we want to start adding at 1 all the way up to 12. And so that answer, again, should just be able to go menu, option 5, option E, all right, 12 trials, probability of success on each trial, 0.06. The lower bound in this case, we want to start adding at 1, and we want to stop adding when we get to 12. And it's 0.524. All right. So that question covers off a lot of different options. All right. Let's move on to the next question. A little bit more involved. There are 2 blue marbles in a bag of 10 marbles. If a marble is selected, it's colored, noted, and returned to the bag. How many trials does it take so that the probability of getting at least 1 blue marble is greater than 0.95? So in this question, it's all in the setup here. So on any trial, you can either choose a blue marble or not a blue marble. And again, on the first selection, probably getting a marble is 0.2. Not getting a blue marble is 0.8. Obviously, there's only the 2 outcomes. All right, and so after 1 trial, the probability of getting at least 1 is 0.2. And really, what we want to do here is we only need to extend the bottom branch because with the wording at least 1, since we're looking for at least 1, it's always the opposite of getting none. So the bottom branch is always going to represent the outcome of getting none. So after 2 trials, probability of getting none is 0.8 squared. All right, and if you think of it in terms of complementary events, if we filled in this tree diagram here, all these other branches would result in at least 1 blue. You notice that every branch would have at least 1 blue in it. So again, this probability here, you can think of as the probability that x is greater than or equal to 1. And in the case of after 2 trials, not getting blue 2 times is 0.64. So the probability of getting at least 1 blue is 0.36. And that's how that works. So again, we can keep extending this blue branch. So obviously 0.36 is not 0.95 or greater. So we keep trying. Every time the probability of not getting a blue is 0.8. So after 3 trials, it's 0.8 cubed. So again, the probability of getting at least 1 then is the complement of that, which is going to be 1 minus 0.512, which is 0.488, which is still not 0.95. And you can see that if we kept going this way, it's going to take a long time to get to the answer. It's more of a trial and error method, which is not really what we want to do here. So let's think of it this way. So that in every one of these cases, the probability of x being greater than or equal to 1, or at least 1, is always 1 minus the probability that x equals 0. Well, we want the probability of x being greater than or equal to 1. We want that probability to be 0.95. And again, if you think back to the question that we did on the previous page, when x is 0, the probability is going to be 1 minus 0.8 to the number of trials. And we rearrange this equation. We get 0.8 to the n is equal to 0.05. And you can either put this in nsolve or logs. Logs is nice. This is going to be n. It's going to be log base 0.8 of 0.05. And that value of n is 13.4. So what this says is after 13 trials, the probability will still not be quite 0.95, so we have to go to the next trial. So n, we have to give it as 14 trials for the probability to be at least 0.95. All right, the next slide is just about expected value. Expected value is very easy if you know you have a binomial distribution, because the formula is just E of x is equal to NP. And so the problem here is, on the day of math test, the probability of a student being absent is 11%. 73 students sit the math test. How many students can be expected to be absent? So it's just NP, so it's the number of students. 73 times the probability of success, in this case being absent, 0.11. Multiply that out, it's 8.03. And again, as we talked about with students, we have to say that this would be 8 students. Can't round up with students. All right, very easy, obviously, with expected value. And the last question here, just a few more distribution type questions in a word format. Tennis player finds that he wins 3 out of 7 games he plays. If he plays 7 games straight, find the probability he will win exactly 3 games. And it's not 3/7. All right. So for A part, probably that, again, we would write this as the discrete random variable is going to be defined as the number of games he wins. Okay, so in this case, it's x equals 3. You could put it into the formula. We look like this: 7 trials. We're looking for 3 successes. Probability of success on each trial is 3/7. And like we say, we're looking for 3 successes. Probability of failure, though, is 4/7. And that would be raised to the number of failures. So obviously, if he's successful 3 times, he has to fail 4 times. And again, this can be you can actually calculate it with the formula that I've just written, or you can use Binomial PDF. It's one particular outcome that you're looking for, and it would be 7 3/7 3. And so on your calculator again, we'll go menu, option 5, option D. The number of trials, 7. Probability of success on each trial, again, you can put the fraction right in to the calculator, 3/7. And the number of successes that we're looking for, that's your x value, is 3. And we okay it, and it's 0.294. Okay. In B part, we're looking for the probability of at most 3 games. So this question is really showing you how to translate wording into the probability notation. So at most 3 games would be x less than equal to 3. But just note too that that could also be written as x less than 4. Right? So those are both equivalent and would both be acceptable ways of writing this. And again, this time we want a range of probabilities, so we want a cumulative calculation. So binomial CDF, it's 7 trials. Probability of success on each trial is 3/7, and we want to add up all the probabilities of all the successes from 0 up to 3. And again, if you do it on your calculator, option 5, option E this time. So the number of trials is again 7. Probability of success on each trial is 3/7, and we want to add up from 0 to 3. So the lower bound we want is 0, the upper bound is 3, and we okay it, and we get 0.653. Okay. In C part, the probability of winning all 7 games. So now it's the probability that x equals 7. And again, this would be a binomial PDF calculation, where it's going to be 7 trials. Probability of success on each trial is 3/7. And we want to know the probability of winning all 7. You can enter that in your calculator. I'll leave that for you. D, let's just look more at the notation now. Probably winning more than 4 games. So the probability of x being greater than 4. Again, equivalent notation to this would be x greater than equal to 5. And again, when you put this in your calculator, it's going to be binomial CDF. It's 7 trials. Probability of success on each trial is 3/7. And you want your calculator to start adding on the 5th win, and you want to add all the wins from 5 to 7. All right. And that calculation, again, it's a CDF calculation, 7 trials, 3/7 probability from 5 up to 7, 0.127. Yeah. Okay. And just for the part E, at least one game. So there you have that at least one again. So again, at least one is probably the x being greater than or equal to 1, like this. Or you can also write it as the probability of x being greater than 0. Those are equivalent again. And again, you can always do the calculation this way, 1 minus the probability that x equals 0. All right. Or, again, using binomial CDF, your entry would be 7 trials, probability of success 3/7, everything from 1 up to 7. All right. And again, you can enter that in your calculator yourself. The last question here asks, after playing 30 games, how many of these would he expect to win? Again, quite easy. The expected value is NP. And in this case, the number of trials is 30. He's playing 30 games. Probability of success of winning each game is 3/7. So this is 90 over 7, which becomes 12.9. And again, with expected value, remember, it doesn't have to be observed. So 12.9 games would be fine answer in this case. All right. So that's how you do those questions in binomial distribution. Using your calculator, try and become familiar with how to use your calculator, both the binomial PDF and CDF features, and when to use them. Thank you.